We're going to start off the day with a very exciting presentation by Gary Demos and Doug Walker. They are going to be talking about core color rendering algorithms for high dynamic range display. Gary is a recipient of 2005 Gordon E. Sawyer Oscar for Lifetime Technical Achievement from the Academy of Motion Picture Arts and Sciences. He's also the founder of Digital Production, Whitney Demos Production, and Demographics. He's also the CEO and founder of Image Essence LLC, which is the developing wide dynamic range codec tech based upon a combination of wavelets, optimal filters, and flow fields. Then Doug is responsible for color technology and software such as Autodesk Flame, Lustre, and Maya. Previously, he was the senior principal color scientist for Eastman Kodak Company in the motion picture division, and now he's very active in the Academy's ACES program. So first, welcome Gary.
Working. All right, good morning. I'm amazed to see all you. I didn't know this time of day had so many of you occupying it. So the basic topic here is end-to-end. So what happens between a camera and a display? And of course, this is complicated by the fact there are multiple cameras usually and multiple display types usually, so it gets to be tricky. The conversion from scene light to display light is really the interesting topic here. And to some degree, it was understood for standard dynamic range, digital cinema at 14-foot Lamberts, and television mastered at 100 nits. But the topic gets more difficult and more issues to contend with when you go to high dynamic range. Okay, so the basic issue is that if you put a scene referred image out of a camera up onto a display without any alteration other than matching color primaries and display formatting issues, that basically you want what appears, at least in standard dynamic range, as a low contrast image to get more apparent contrast. That doesn't necessarily mean a gamma boost or a simple contrast function. It's in general a more complex topic than that. So there are two systems out there that are widely recognized as offering an end-to-end idea. One is the hybrid log gamma optical to optical transform, so OOTF. And there are actually two transforms in BT 2100. They're both similar with different strengths and variations. And the other one is ACES. That's the one that I've had involvement with and Doug has had involvement with. And the ACES system has a model for going from scene light to display light. But there are issues with these. The OOTF for hybrid log gamma is basically a simple gamma, and that works within certain ranges, but it is difficult to extend it. The hybrid log gamma also has the property that with respect to neutral, it darkens all colors, mostly blue, but all colors, yellow, green, anything. So that's an unusual behavior, I think. It's not part of what systems like ACES do. So the ACES system, there's some issues in ACES 1.0 that have been recognized, and so there's now a consideration of going beyond it. But the system has interconnects that make it a little bit difficult to tune it and work on it. And so we're trying to isolate that out. So I've had an architecture that I've been working with. Across the top half of this slide is ACES architecture for, I believe, every released ACES uses that architecture. And below the central line there see if this laser, the wimpy laser, wimpy. Okay, well anyway, below this line, if you can see that, is a different version of that. It's been put into more modular blocks. The reference rendering transform of ACES is up here. It's mandatory, and it does several things at once in a kind of a combined manner. I have split that out. The second part of the split out is where this gamma issue is handled. In other words, the scene tone curve to the display tone curve, and we're proposing that be mandatory. The looks, it just doesn't seem possible to have a common unified look. So there are many possible looks. We have some example looks, and you can even bypass all those and just do everything in grading. So the topic here is really this piece. It's the mandatory piece, and so we felt it was important to get that one right. Now, coming out of that, instead of multiple output device transforms matched to specific device types and signals, there's a single module which is parametric, and the parameters come only from the display. They're not coming from upstream or metadata. They're only coming from the output side. So they include the display's brightness, its ambient surround, those kinds of properties. Then there's a display formatting, so you put gamma on it, the display takes gamma off of it, you know, those sorts of things. So the ACES on the top here is using S-curves independently for red, green, and blue. And if you look at the relationship of red, green, and blue, when that happens, for example, if I take orange, near the bottom of the curve, orange is going to push towards red and desaturate. Up a little bit, it's going to boost saturation and push towards red. Up a little further, it'll boost saturation and push towards yellow. And then up a little further yet, it'll desaturate. So the behavior is intertwined with the neutral spine behavior. So in the nugget, we're making hue and saturation have no alteration in the radiometric sense. In other words, if you put a chromaticity meter on it, it would not be altered on one side versus the other, which is clearly not true of this. So we split the RRT logically. There are optional aesthetic rendering preambles, that's what I'm calling them, or none. They're all optional. It could be just done with grading. We made the nugget tone curve process mandatory because you need that. In all cases you need it, and we thought that should be isolated out and be the centerpiece. And we put the master between these at the input to the tone curve nugget process. So in the ODT, we've split that into device-specific formats. It's not really an ODT. I use my own words, but it's two pieces now: parametric appearance compensation, which is an example. It's not normative. None of the aesthetic preambles are normative. They're all examples, or you can use them if you want. And then the device-specific formatting with the back half, which is not intended to change appearance. It's just intended to get the format in the right state so that the display puts up a no-op, basically, within its range. Okay, so that's what it looks like if you just put that all in one slide and say, okay, so it takes typically ACES AP0 primaries with an IDT of some sort, and then that makes an ACES RGB and AP0 primaries, usually EXR half-float format RGB. The split processing here, these preambles are isolated from the tone curve, parametric appearance compensation, display form. Now, it's possible to lock down the chromaticity all the way from here, which says if I have known chromaticities at the camera, I can have known chromaticities matching that at the display. This has amazingly great benefits for both debugging the architecture, which can get complicated, and also calibrating everything. Okay, over to Doug.
Thank you, Gary. We seem to have a little bit of a stray light problem up here. I don't think the Dolby folks would approve of this theater configuration, but so I'm going to focus on what Gary was showing as the rendering nugget, and which we're also calling the core rendering transform in our paper. And I'm going to start with the neutral scale behavior of that, which could be called the core tone curve or core transfer function. And as is the tradition in image science, I'm going to show you some graphs on logarithmic axes. And so what I'm showing here in the red curve is the neutral scale performance of the core rendering transform. And the horizontal axes are logarithm of ACES values coming in, and the y-axis is the logarithm of the luminance produced by the display. And in this case, we've normalized that to the 48 nit reference of standard dynamic range cinema. And for comparison, we are showing some of the ACES tone curves as well. So the dark blue curve is the system tone scale for standard dynamic range cinema in the ACES system, and it has the characteristic S-shaped curve that you expect from not only ACES, but motion picture film and other successful imaging systems. And you can see that we're plotting a very wide range of log exposure values or log ACES values on the x-axis. And so that's why you see that the standard dynamic range curve plateaus in the very dark and very bright areas. The green curve is the ACES RRT, and you can see that continues across a wider range of exposure values, and that's kind of our reference here. Our tone curve is basically modeled after the ACES RRT. The central region of that curve was very extensively tested by expert viewers, including members of the American Society of Cinematographers and others. So we were trying to follow that curve, and in particular, we're adopting the same placement of gray, which is 18% gray at 10% of the SDR white point. So we're similar through the mid-scale. The differences of our tone curve are at the extreme ends. So in the very bottom end, we extend as a gain factor, and at the top end as well. And this makes the curve more invertible. The other thing that we did is that we decided we would place ideal diffuse white, in other words, an ACES value of 1 at the SDR display white. So map 1 to 1. The ACES RRT goes through at a little bit brighter point than that, but we figured mapping 1 to 1 is a useful reference point, and it facilitates comparison with other systems, which people talk about a lot. For example, in video, a lot of people talk about using just a simple gamma as the OOTF or as the rendering function. And you know, if that's something that is going to pivot at SDR white, then for HDR, it's obviously not going to work too well, in the sense that there's at extreme, at values above 1, you get a huge gain boost. In our paper, we have graphs on linear axes as well, such as this, which you can look at for reference. Obviously, it's not as illuminating as the log axes, so I'll let you look at those in the paper if you're interested. One of the things that we did in optimizing the core tone curve was look at the slope or derivative, and on this graph we have the same log ACES x-axis, and on the y-axis we're showing the slope in log space. And you can see that the green curve, which is the ACES RRT, the slope goes to 0 at either end, which means that it's essentially not invertible in those places. So we put a lot of effort into making sure that the slope was a nice unimodal distribution. You'll notice that there's a sort of a piecewise linear characteristic to the slope, and that's due to the use of quadratic B-splines. The corners there are essentially changes in the second derivative, so they're not visible to the human eye, but they look a little bit odd when you graph them. And you know, we use the same quadratic B-spline technology as is used in the ACES system, and that facilitates easy adjustment of the tone curve, and it allowed us to place precise constraints on both the slope and derivative of the function. Now I'll talk about the color handling of the core rendering transform. So as Gary pointed out earlier, if you think about how colors go through a conventional tone curve where you're applying the S-shaped curve independently to red, green, and blue, what we're showing here is if you imagine a shadow to highlight series of the same orange color, in the shadows and in the highlights, the red, green, and blue get closer together, so the ratio between the channels gets closer to 1, and hence the color desaturates. In the mid-scale, the saturation is boosted. In the lower part of the curve, the green essentially gets closer to blue, and the hue shifts towards red. In the upper half of the curve, the green gets closer to red, and the hue shifts towards yellow. Another issue with applying tone curve in a conventional way is that the results that you get in terms of these hue and saturation changes depend on the primary set that is used to apply the curve. And so in this example, I'm showing applying the same tone curve in both cases using Rec 709 primaries on the left and ACES 2065-1 or AP0 primaries on the right. And you can see, for example, in the orange of the pepper gets more saturated. Well, I should say, I hope you can see. If you look at the PDF, you'll see. The orange gets more saturated. The blues change hue a little bit and get more saturated as well. This is something that we experimented a fair amount with during the development of the ACES system, trying to find the ideal primary set, and it's a difficult challenge. Some of the hue and saturation adjustments that you get from particularly the saturation adjustments you get from the S-shaped curve are actually useful. For example, the property of desaturating in the highlights is useful, but in general it's difficult to control. And in addition to that, there's also the problem that values outside of the rendering primaries typically get clamped. And so because of all these limitations, we wanted to investigate what are called ratio-preserving tone curves, which provide a way around some of these limitations. So on the top, I'm showing the conventional tone curve where you apply the S-shaped curve to the red, green, and blue channels independently. And on the bottom, we're showing the ratio-preserving tone curve. The idea here is that you combine red, green, and blue into a single number using a function we call the norm, and you send that through the S-shaped curve. Take the ratio of the input and output of the S-shaped curve and use that as a gain factor on the red, green, and blue channels. And if this is done in linear space, as we are, then you're essentially just applying a gain factor to tristimulus values, and so therefore the chromaticity doesn't change, and so to a large degree the hue and saturation also do not change. So a norm is a term in mathematics that refers basically to a way of calculating distance or length of a point in a multidimensional space. So it's a way of converting RGB into a single number. And there are various, the key to having a good ratio preserving tone curve is basically to choose the right norm for it. And different things that people have experimented with over the years are luminance, maximum, and ratio of powers. And I'm going to talk about some of the challenges, and in particular the brightness of colors with respect to neutral. So whether you're using a ratio preserving tone curve or a conventional tone curve, the neutral scale is exactly the same in both cases. It's really the color, it's what happens to the colors that are different. And if you think about converting RGB into a norm using luminance, you have 0.3 times red, 0.6 times green, 0.1 times blue roughly. So the red, a pure red, is going to go through the tone curve at 30% of its corresponding neutral, and blue at 10%. So all of the colors get darkened. And as Gary pointed out earlier, this is something that happens in HLG, Rec 2100 hybrid log gamma, for example. On the bottom, we're showing the norm that I'll describe in a minute. And you can see that the colors are maintained at a better brightness relative to neutral. Another issue with choice that's related to the choice of norm is the noise issue. So if you think about using the maximum, if you have like an off-white color that's a little bit yellow or a little bit blue, on the yellow side, red or green will be used for the norm, and you'll get the good noise properties. If blue is maximum, then you get the noise properties of blue, and that essentially couples blue noise into the other channels. And so on the top, you'll see the max norm is noisier than the weighted power norm. So the weighted power norm is something that was suggested during the ACES development by Lars Borg. And it's a very interesting idea. It solves the neutrals and color problem. If you think about a value of NNN and you calculate the norm of that, you get the same thing as you would for N00, which is just N. So reds and neutrals would go through the tone curve at the same point. But from a noise point of view, it's not ideal because it's similar to the maximum in the sense that the largest channel tends to dominate. So what we're proposing is what we're calling the weighted yellow power norm. And in this case, we've weighted the channels. These coefficients were determined in AP0 space. And they essentially give the noise behavior of a luminance norm, which is good, with the nice properties of preserving color ratios relative to neutral. And also, in this case, we're brightening yellow and darkening blue somewhat, which we feel gives a nice effect. And it's something that was also done in the early ACES systems, going back to the work of Mitsuhiro Uchida and his colleagues. So to talk about the details of the algorithm and inversion, the first step is to calculate the norm. Second step, to send that through the S-shaped curve. Third step is to calculate the ratio of the input and output of the tone curve. And fourth step is to multiply that by the red, green, and blue channels. And so the inverse looks very similar. You calculate the norm of in this case, the display referred values, send that through the inverse of the tone curve, and the quadratic B-splines are quite easy to invert. Calculate the ratio and then multiply. I guess the trick to seeing why this inverse works is to think that, if you look at the forward, we're applying a gain factor to red, green, and blue. And so if we can just recover that gain factor, then we can invert the function. And if you look at the norm, if you think what happens to applying a gain factor to RG and B, you'll realize that the norm of a gain times an original color is equal to the gain times the norm of the original color. In other words, the gain factor factors out of the norm. And that's why the norm that you would calculate, the norm that's coming out of step 2 here is going to be the same norm that you would calculate after step 4. So Gary has a very sophisticated program called the sigma compare, and we did a very thorough exploration of the inversion capabilities on very large and negative numbers and so on, and it inverts precisely to within like a 1/1,000,000th. In summary, the benefits of the core rendering transform are that chromaticity is preserved, and hence hue and saturation are mostly preserved. It has a robust, straightforward inversion and good noise properties, and it has an optimized B-spline tone curve based on the ACES RRT, but more invertible and more suitable for HDR. Finally, we'd like to acknowledge the work of the Academy in developing the ACES system and for bringing together such a talented group of people to collaborate on the design of it. We certainly benefited a lot from our interactions with this group of people, and benefited from having this foundation to build upon. And that's our talk. Thanks.
Thank you very much. So now I'm going to open it up to questions. And as people are preparing their questions, I have one to start with. In the conclusion, you mentioned noise properties. Can you elaborate a little bit? Because you didn't touch too much on that in the actual presentation.
Do you want to? Right. So the norm is, in choosing the norm, that's one of the criteria that one needs to look at, is what are the noise properties. And luminance, because it weights red and green, which tend to be lower noise, higher than blue, has better noise properties than some of the other possibilities like max. Some of the earlier ACES systems used something called the Hewish-Dorr algorithm, which also had similar issues to a max-based norm in that it allowed blue noise to couple into the other channels. So that's something that, yeah, we looked at carefully.
Okay. I guess another question from me. Are there cases where it didn't work as well?
As well as?
You expected. Is there room for improvement in the future, or is this it?
I think there's definitely room for improvement. What do you think, Gary?
This is the 2.0 forever.
Great answer. And then the last question also, which primaries did you choose? Why? Also, did you test it? Because the norm would be different for different types of primaries that you would choose. Yeah,
it's a good question. The weights for the norm were based on the AP0 primaries. And, but it's important to point out that the ratio preserving tone curve is less sensitive to the choice of primaries. That's one of the challenges that we found in the development of ACES, is that it was difficult to find a primary set that was perfect, and if you change the primary set, it kind of means retuning a lot of other parts of the algorithm, whereas the ratio preserving tone curve is less, it doesn't clamp values outside of the rendering primaries, and it's not as sensitive to the specific primary choice.
Okay, thank you very much.